In this video, we're going to look at another technique of integration, which is called integration by parts. And it's basically derived from the product rule for taking derivatives. And as usual, you always want to use the basic techniques before you use this one. Okay, so your basic u substitution, or if it's a simple integral, just go ahead and use that, because this can get complicated if you use it when you don't need to use it. So to start off with, look at the way this is derived. I have the derivative of u times v. U and v are functions of x. So the product rule tells you it's the first function u times the derivative of the second, so u times v prime, plus the second v times the derivative of the first. You get vu prime. Okay, so then multiplying that by dx, okay, we wind up with this situation. And then I go ahead and take the integral of both sides. Okay, here I'm going to break it up into two. So I'll put integral here and integral here. And then I solve for this one right here. So the integral of uv prime dx, taking this over to the other side, I wind up with the integral of the derivative of uv, which of course will give you uv, and then minus the integral of v u prime dx. And this is your main formula. Okay, so you start off then, say in the first example that I have here, have the integral of x squared ln of x dx. Okay, so the way that stands, there's no basic formula or basic u substitution that's going to work here. Okay, now just to say example, if this were ln of x, say over x dx, then your basic u substitution is going to work here. You would just let u equal to ln of x. So du would equal to 1 over x dx. And then you just make your substitutions here. Okay, or over here I should say. Okay, the dx, notice that dx over x can be replaced by du. Then this actually can be written as u du. Okay, which you can easily integrate. Have a u squared over 2 plus a constant. All right, u squared over 2 plus a constant. And then you just replace the u by ln of x. So the answer would be ln of x quantity squared plus a constant, over 2 rather, plus a constant. Okay. This case, that's not going to work. Okay. So the integration by parts simply tells you then, you look at the integrand right here, and you look at that as two functions. One will be u, and one will be v. And you want to select your u and your v appropriately so that you can write this in terms of another integral. Okay, for example, this one right here in the formula, that makes it easier to integrate. Okay, and what do we have here? Okay, so generally what we want is we want v to be the more complicated of the two functions, and you can easily integrate. And you want u to be a function that's easily differentiable. Okay, you can easily take the derivative and simplify it. Okay, so when we take the derivative of u, it will simplify. Okay, so in this case, the only choices you have is that u would have to equal to ln of x. Okay, because ln of x by itself is not easily integrated. Okay, so you can't really take the integral of ln of x. You can take the derivative of it, Okay. For x squared, you can take the derivative and you can also integrate it. Okay. So again, generally pick u so that you can easily take the derivative of. Pick v so you can easily integrate it. So the only choice we have here then is u then will be ln of x. So I take the derivative of that, and that's going to be 1 over x. V prime then would be x squared. Okay. And then I take the antiderivative of that, and I get x to the third over 3. Okay. We don't mess with the constants of integration here because we put that at the end of the problem once we have the final solution. Okay. So in this case then what we'll do is use the definition over here. Okay. So this is the original integral here, which is not easily integrable. So we write it in terms of another integral that we hope will be simpler. So just based on what I have here then, u and v, once you select it, the first step then is to simply plug in. So u is ln of x. And just so there's no confusion here, I'll put that in parentheses. That's going to multiply v. So you can put it here on the left front. On the right doesn't matter here. X to the third over 3. Okay, and then I have a minus. And then I have the integral of, this is v. Okay, so here's v. That's x to the third over 3 times u prime. Okay, u prime is 1 over x. So this will be times 1 over x dx. And the idea here is that you're hoping that this will be easily integrable. So this is going to equal to ln of x then times x to the third over 3. And let's simplify this one here. This will be antiderivative, or the integral of x and x cubed reduced down to x squared over 3 dx. Okay, right here. And then we're ready to take the antiderivative of that. Okay, so this would be then ln of x, and I'll put that out in front so I don't have to put parentheses. X to the third over 3 minus, and then we integrate here. Add an exponent here, add 1 to the exponent and divide, so this will be x to the third. And then the 3 in the bottom, 3 times 3 will give us the 9. And then we add our constant of integration, c. So this will be the final answer. Okay. Now I want to make a few points here. Is sometimes when you're dealing with this procedure, you're going to have a repetition. Integrals like, say, integral of, say, x to the fourth e to the x dx. So the x to the fourth you can take the derivative of, you can take the integral of, e to the x, you can take the derivative, you can integrate, no problems there. But if we let u equal to x to the fourth, then du would be, or u prime would be 4 x to the third. And we're going to have an integral of the same type again. It'll be e to the x and e to some x to some power, and then a constant over here. So you might have to use integration by parts several times before you have the correct answer or the final answer. Or if you have an integral like, say, e to the x sine x, Again, if you let u equal e to the x, v prime equal sine of x. No problems as far as the operations go, but this is just going to repeat. You're still going to get an e to the x, and the next one might have a cosine, but you'll have to repeat it. And there's ways to handle that type of integral there. Okay? So you can have problems where you'd have to use integration by parts several times before you get the same answer. Or you might have one where it repeats, the original integral repeats, and you do a little bit of basic algebra to solve the problem. So we'll consider some more examples on future videos. And again, I'm going to give you a final answer over here, written in this form, in case you can't read the writing. But anyway, this is the final answer to this particular problem. Okay, thanks for watching. We'll see you in the next video.